Let's get started. Welcome back. Happy Monday. A few administrative things here at the start of this class because there's kind of a lot happening in our class this week. So first of all, test corrections are due Wednesday at the start of class. If you finished them, you can throw them in the folders today, but otherwise Wednesday, start of class for test corrections. Project number 4 is officially assigned. It is on your table, so make sure you grab one of those. Before the snow days, this project was due before our spring break, which is coming up. But because of the snow days, this project is now due the Monday when we return from spring break. So 2 weeks from now is when this project is due, okay? Your grading choice was due last Friday, but that was when I thought I was going to get the tests turned around a little bit quicker than I did. So at the moment, the grading sheet is going around. Where is it right now? Let's pass it to another table. So all you're going to do is circle one of the grading options there or write in your own personal grading option. The rules are all on the sheet. If you don't know how you want me to grade you as of today, I'll take it on Wednesday, but if you know, then go ahead and fill it in right now. Also coming up on Friday, quiz number 3 is due. This is yet another take-home quiz. You don't have it yet. I'll give it to you on Wednesday. Okay, so we'll give you a quiz Wednesday. You'll hand it back to me on Friday. And then something that isn't in the calendar, but is a response on my part to some of the issues I saw on the first test that we just took, is that some of us are really, really good at U substitution, and many of us are not. And I need us to practice more with U substitutions. And so I'm going to give you another take-home quiz. I'll hand it out on Friday. It's just going to be a collection of problems from your textbook. It's going to be some even numbered ones because I don't want us looking at answers for this one. So I'm going to hand that to you on Friday and ask that you work on it a little bit over break and hand it back to me when we come back, okay? So that's not in the calendar here, but it's, like I said, a response on my part to some concerns I have about U substitutions. I think it's really important enough to warrant a separate quiz. If you know U substitutions, it's going to be easy and you will get through it very quickly. If you don't know U substitutions, then you need to practice on it, and it's going to take you a while, and that's okay, because you need to get better at it. All right, so more details on that on Friday. I'll hand it out then. Any questions on any of the calendar stuff? Okay, so let's jump in. Yeah, it's on the table. Where are the projects that are on this table? Everybody has a project? Okay, good. All right, so let's take a look at our daily summary. Let's see, can we go to Zach for the summary? Okay, so the first integral we're going to tackle today looks easy, at least in terms of the integrand. 1 over x squared, piece of cake. It's just a power rule. What's new in this integral is the infinity. So we're going to deal with things like this today. Just to give you some motivation as to why we might ever care about an integral going out to infinity, like what does it even mean? Okay, so here's the picture. This is the graph of 1 over x squared. If I say find the integral of this function from 1 to infinity, what am I calculating geometrically? Area from where to where? From 1 to infinity, meaning forever, right? I'm asking you to find the area of this infinitely long shape, but it does get really, really thin the farther out you go to the right. Okay, so that's what we're after. But like I said, I'll give you some motivation here. So one of our upcoming projects, I just handed you project 4. This is part of project 6 that I'm projecting. I'll give it to you at some point. But it talks about this loan that West Germany made to the former Soviet Union. The Soviet Union had some natural gas in Siberia that it wanted to get to the rest of the country. But it didn't have the money to build the pipeline connecting Siberia to the rest of the Soviet Union. Western Germany had the money, but they didn't have any of the natural gas, and they wanted that. And so a trade was struck. And the details are here. You don't need to look at them right now. Suffice it to say, West Germany made the Soviet Union a loan, money, and in return, the Soviet Union is going to provide natural gas to West Germany, not just next year, not just the next 10 years, but forever. This was a deal forever, for the rest of time, Soviet Union was going to be pumping a certain amount of gas over to West Germany to pay them back for this loan, okay? And so you're going to work through the details of this in the project. But it turns out that an integral is the appropriate way to tackle this problem. That should not be obvious to you at this point. But the forever part means that that top limit of the integral is infinity, okay? And so let's talk about how we handle infinite limits of integration. Okay, part B says, suppose that we replace the infinity with a b. Don't even worry about the fact that it's infinite. So let's just tackle this guy first. So this is equal to integral 1 to b. I'm going to rewrite this guy as x to the negative 2. And then I can do my power rule. So x to what's the new power? So negative 1 or negative 3? Negative 1. Got to be really careful. Add 1 and then divide by the new power. Right? And then we're going between 1 and b. I'm going to rewrite this guy just so it's a little bit more friendly for me. So would we agree that's really negative 1 over x? Okay, and then we'll plug in the 1 and the b, and so we get negative 1 over which one goes first? B, right? Top guy goes first, and then what's the symbol? Let's subtract, and then we plug in the 1, right? Negative 1 over 1. So I'll clean that up just a little bit. Negative 1 over b, and then plus 1. For some reason, I do have an extra packet. Is there anybody that's missing one? Thought I printed exactly the right number, but yeah, the big packet. I just want to make sure everybody's working through a big packet right now. Okay. All right, so no funny business, right? We just did an antiderivative and plugged in top and bottom and subtracted. We got this. So what does this integral represent geometrically? This integral from 1 to b. 1 to some point b, right? So like some kind of generic stopping point, we'll just cut it off at some number b. What do you think we're going to do to b to answer the original question? Limit as b goes to infinity. It's what really natural to do, right? Just let the b go forever now that we've dealt with the antiderivative part. So here is our notation. And you guys know by now I'm a big fan of notations. So leave a little space in there. Integral from 1 to b. 1 over x squared dx. That's the integral we just found. But what goes in the front? That's how we write it. Right? This is our definition for how we handle an infinity on an integral sign. What's that? You do, yeah, right? You just change the infinity, which is a problem, to a letter, which is no problem. And then you do it normally, and then take a limit at the end. Yeah, if the graph doesn't approach 0, then the answer might be infinity, or it could be like an up and down kind of thing. So we need it to approach, we need this limit to exist in order for the integral to exist. Mm-hmm. Yeah, if it were a minus infinity at the bottom, yeah, just place the minus infinity with a letter and then take a limit. So what the graph does is kind of independent of what the b does. Like the graph is just going and we're saying, let's calculate the area up to b. Yeah, it's always going to infinity. All right, so I think we're good here. Okay, so what did we discover up above? This was negative 1 over b plus 1. Is that what we calculated the integral was? Okay, and then we have a limit. And we take our limit by sending b to infinity. And what happens to this guy right here when b gets really big? Goes to 0, right? And so what is the limit? 1. So that's the answer to this original integral. Which, if you think about it in terms of area, is kind of a surprise. Because what we just discovered was that the area that's shaded in there in green, if you go forever, is exactly equal to 1. doesn't actually ever get to 1, right? Like if you plug in b equals 100, just picking a big number, then what is this equal to? It's 0.99. And if we plugged in b equals 1,000, it'd be at 0.999. Never gets there, but in the limit, it's as close to 1 as we could possibly hope for. So what else could we call it other than 1? And notice that like going from 1 to 100, what's that? There's no running out. No, this is yeah, we've got infinite supply here. It's great. And notice that if you go from 1 to 99, 1 to 100, what did we say the area was? 0.99. And then you go from 100, where we just stopped off, all the way to 1,000. Now it's 0.999. We've only gained an extra 0.009, right? So like this is something that it takes a long, long time. Yeah, Cooper. All right. We can argue later. Okay, so that's good there. Number 2 is basically a definition that just kind of summarizes what we did. If you see an infinity, change it to a letter and send that letter to infinity. Rob had asked about this other one. What if it's minus infinity? No problem. Change it to a letter, send that letter to minus infinity. If the limits above exist, then we say the original integral converges. That's a word we'll be using a bunch. So that integral that we just started with converges. It converges to the number 1. That's what we found. But if the limit doesn't exist, either because it's infinity or because maybe the thing oscillates and doesn't actually narrow in on a unique value, then we'll say the integral diverges. Okay, converges and diverges. So like there's this like trilogy, Veronica Roth, I think is the author, Divergent, isn't that the first, right? And then there was a movie. Yep, I watched it and looking for integrals that went to infinity. Nothing. Always disappointed by the Hollywood machine. Does not converge. It is. It is. Yeah, divergent or does not converge, same thing. Okay, next page. Take a look at this guy. Integral from 0 to 1 of the square root of 1 minus x. This one seems to be no problem at all, right? It's just a basic old integral, no infinities on the limits. So where's the problem here? Yeah, if we end up dividing by 0, we've got issues. And what value of x is the bad one? It's 1, which happens to be one of our endpoints. So it doesn't look like it's a problem, but it is. And so what we'll do is change that problem number to a letter. We'll do this ordinary integral. Limit as b approaches 1. Fair? Okay. So let's do this guy right here. All right, so I'm going to put the details up above, but this is a u substitution here. What's a good choice for you? 1 minus x, and so then du is negative 1 dx. Okay, so then this guy becomes integral from 0 to b. Actually, I'm going to, I don't know what I'm going to put here. 0 to b. I'm going to write this as 1 minus x to the negative 1/2 power, right? It has nothing to do with the u. That's just rewriting it as a power. And then we're just going to do this u substitution without all the details here, knowing that the answer is just going to be the negative of what we might expect it to be. So add 1 to the power. What does it become? 1 minus x to the 1/2. Divide by the new power. Divide by 1/2, which is the same as multiply by 2. This would be the answer, except the derivative here was negative dx. So there's like this extra negative 1 that we have to account for. So the answer is really negative 2 times that stuff, going from 0 to b. So I don't need you to be able to do the u substitutions essentially in your head like we did. Just got to get to the answer somehow. And again, that take-home quiz I'll give you over the break will hopefully give us more practice with u substitutions. Okay, so before I plug in, I like to clean up my powers, so I'm going to write that 1/2 as a square root. So this is negative 2 square root of 1 minus x, going between 0 and b. So negative 2 square root of 1 minus, what goes first? b. And then subtract -2 square root of 1 minus 0. Okay, so I'll clean this up just a tiny bit. This equals -2 square root of 1 minus b, and then altogether this is just a plus 2. Is that all right? Okay, square root of 1 is just 1. Okay, so we've done our integral, no problem. And now we're not sending b to infinity. What do we need to send b to is 1, right? That's what we replaced initially with the b. So this guy equals, what are we doing here? Limit as b goes to 1 of the answer we just came up with. Is it? So the first part is 0. So the whole thing is 2. Is that okay? Send b to 1. Rich, is that all right?
Yeah, I agree.
Okay. Okay, so that's our answer there. All right, despite the fact that I reminded you to remind me to check our answers on the calculator, we all forgot, so let's try it now. Okay, so I'm going to go into, and you can do this later on, but Math 9 is our integral thing. So we're going to go 1 divided by the square root of 1 minus x, parentheses there, comma x, comma 0, comma, okay, so the original was supposed to be 1. All right, I don't know whether or not I should try it. I guess we'll just try it anyway. I'm hoping it doesn't like it, but I mean the fact is it's just going to be approximating stuff, so maybe it'll be okay. I'm not sure. It shouldn't be okay, but it's an imperfect science here. All right, so one thing I can do is tell it to stop fiddling around and pretending. There we go. All right, pretending it's, you know, like it restricts to actual speed. Okay, so so it didn't have a problem, even though it should have. So that was kind of anticlimactic. I guess what I would suggest that we do instead was put in something just close to 1, and then let it do its thing, and not be surprised when we get an answer that's close to 2, right? Restrict. There we go. 1.98. Right. And the closer to 1 we put our answer, the closer to 2 the output will be. So that's pretty compelling that 2 is reasonable there. And then we can do the same thing on the first integral we did, right? Which was Math 9. So what was the first one? 1 over x squared? 1 over x squared, comma x, comma, from where to where? 1 to, okay, so I can't see if the calculator is able to do this because I don't have an infinity symbol. So what should we put? 10,000. Great. And remember, the answer that we got was how much? Was 1. So we're expecting something close to 1. Now 10,000, I suspect it should give me something close to 1. All right. So the problem is when you leave it on fast speed, it auto shuts off in 5 minutes in fast speed. And that's what happened right there. Okay, so there you go, 0.9999, which is pretty compelling that the right answer was 1 if we go forever. Okay, so you could always check these. So what I'll be looking for is the calculus way of doing things. Okay, we're not going to do this one, number 6, but just one quick final example. Where is the problem with this integrand? Is it x equals 2? That's where we divide by 0, right? But hey, it's only 1 and 4, so no problems, yeah? Yeah, it doesn't exist somewhere in that interval, right? So like I can't think about just like ignoring the fact that 2 is a problem. I'm sweeping out area from 1 to 4, but there's this major hiccup at x equals 2. Maybe, I mean maybe. But what we need to do is actually split this guy up into 2 integrals. Integral from 1 to b. And then the integral from a to 4. And what are we going to send b to in this case? Send B to 2 here. That'll take me from 1 to 2. And then what are we going to send A to in this case? Also 2. And that'll take me from 2 to 4. And then we add those two things. You don't like that? Talk to Caitlin. Talk to Hughes and Howard as well. Okay. So the good news is these aren't all that tricky to work with. It's a pretty straightforward technique with a little bit of practice, no problem. The bad news is that we've just added something to your list of responsibilities. And that is anytime you have, okay, so like if there's an infinity up on the integral sign, you'll recognize, oh, it's from that class where we had the infinities on the integral. But if it's just the integral from 1 to 4, there might not be any like buzzer going off in your head. And so now I'm telling you that you need to add to your list of buzzers that go off in your head to always check to make sure that there's no problems inside of that interval, right? In this case, 1 to 4. Mm-hmm. I think ultimately you can often get the wrong answer. If you just naively just ignore the problem in the middle, you'll get it. You'll get a number. No, but yeah, but like you'll get a number, and the number could have nothing to do with reality. And so like it really is important. This isn't just like you know, like on a math test, you got to recognize it. It's that you'll get deceptive answers. They'll just be flat wrong if you don't. Yeah. Because if you did this, that's right. If you did it when there's no hole, it'd be the same answer. But here we're going over a vertical asymptote, and funny things can happen. Okay, next page is where the activities start. Hoping that we can get through all the activities and maybe even a good chunk of the even more practice section. Raise a flag if I can help.